Okay.
Hello, everybody. We're team number 44, and our project is mosquito species identification. My name is Sudarshana.
My name is Kartika.
My name is Grant.
So the motivation behind our project was to distinguish between the two species, pipiens and restuans. As we all know, mosquitoes have always been like disease carriers, and so far the methods used to distinguish between them have been very laborious and intensive. So the motivation behind our project is that we want to make an effective classification between the two, and also we would like to determine if there are any physiological differences between the two species.
So the data set we're using was collected by the entomology lab of Chris Stone at the University of Illinois. It's of two species, high resolution images of their wings, accompanied by class labels. So these two species, you can see an example of each species shown here. Their wings are very, very similar. In fact, they're so similar that we do not know if there exist differences between their wings physiologically, but there's precedent for such differences between species in the entomological literature. So we're going to try to find what are there, because the data set was prepared for the specific purpose of using machine learning techniques to try to identify differences between the mosquito wings.
So the first approach that we tried was the transfer learning approach on VGG19. As we all know, VGG19 is pre-trained on the ImageNet dataset. So one of the reasons we chose this was so that we already have a model that would be trained on a really large network. So the weights would probably be something that would give us a good classification. So in our model, what we did was we kept all the layers of the VGG19 constant and added 3 dense layers in the end, which were the only trainable layers of the entire network. And the last dense layer had only two neurons and an activation of softmax. So these were the distribution of the training and testing data for the VGG19. And these were the specifications. And after adding the dense layers, which were the only trainable ones, we got the specified parameters. However, this method was not effective at all because we got only a 25% testing accuracy.
So the next method we tried was an automatic feature extraction approach. So essentially, other mosquito species distinctions have been found in the placement of the points at which the veins branch, and more macrostructural things than ImageNet trained classifiers are usually used to looking at. So we used a Harris corner detection algorithm, which basically finds the likelihood of being a corner, or assigns a corner score for each pixel of an image on each image in the data set. And then we took the most probable corners from that algorithm and fed them into a K-means algorithm with K equals 80 on those points to find 80 pairs of XY coordinates that correspond to the most plausible corner points for the image, as you can see in this example. And we also augmented the data by flipping it horizontally. So we fed these into a 2D convolutional network, essentially as a skinny image with these specifications. As a result, we found that it performed better than our baseline, which would be around 50%, but not by much, only by around 1 to 4% whenever we ran it. Additionally, as you can see, the validation loss is going up, and it seems to be overfitting a lot to somewhat irrelevant features. It's good at the training set, but not great at the validation set. But it does perform better than the baseline. So it was a moderate success, if not all that exciting.
So when we recall the images of the two wing structures that we saw in the earlier slides, namely the culex pipiens and the culex restuans species, we will never be able to visually distinguish between the two structures because they are very similar. So we tried to go towards the convolutional neural network approach. Because of the property of dimensionality reduction at every layer, the convolutional neural network is properly able to identify the underlying patterns existing between these two species, these two images. The images of these two species. So the we split our training and validation data sets in a 75-25 ratio, and we ended up with around 795 training images and 265 validation images. We used the Keras library to construct our neural network. The architecture that was employed was very straightforward and simple. We used 2 convolutional layers, which was connected to a fully connected layer. The output neurons were just 2 because of the 2-class classification. We use the categorical cross entropy as our loss function, and we use the Adam optimizer to go along with it. We got an accuracy of 68% when we trained our network. When we observe the loss plot, we can see that the training loss increases, and a proper learning rate has been employed. We believe this has happened because of the reduce on plateau callback feature that we employed. Whenever the validation loss seemed to plateau, we decrease the learning rate. We can see that the validation loss keeps increasing, which was not desired. The accuracy graph shows that there is the validation accuracy and the training accuracy have a very large gap between them, which means that our model has been overfitting at some point. This is probably because of the data ambiguity. We have less than 1,000 samples to train on, and the data is very closely correlated with each other. However, because the overall accuracy that we achieved was 68%, which was well above the benchmark that was proposed, which was 50%, we believe that our task has been successfully accomplished. Thank you very much.